Hello and welcome. This is the fifth in a series of lectures covering chapter 15. So we're going to talk about the physical pendulum, which, as you've seen in the previous part, we talked about a simple pendulum, and now we moved on to a more generalized case. So essentially, you can take any object and rotate it around a particular point. So the way that you can describe the motion of any object that's sort of swinging about a pivot point is based on a bit of rotational kinematics. So first of all, you need to establish where your pivot point is, where the center of mass is, and know the distance between the 2 points, as well as knowing the moment of inertia of the object. Now, moment of inertia, you may remember, is sort of the rotational equivalent of mass. It's how much an object likes to stay in motion or resist a change in motion. So the idea is that when an object is sort of hanging as if it were a pendulum, then there's going to be a component of its weight of gravity that acts as a restoring force. This is part of the derivation in the textbook because we're talking about rotational dynamics. It's easier to work with torque. So in that case, rather than talking about a restoring force, we talk about a restoring torque. So the restoring torque is in fact this very basically horizontal component of the weight times the horizontal distance to the pivot point, right? That's the definition of torque. The force times the it's a cross product between the force and the distance to the pivot point. And at the same time, though, if you recall the rotational equivalent of Newton's second law, this torque is then equal to the moment of inertia times the angular acceleration. So it just follows from here then that when you have a small angle, you can rewrite the formula, this restoring torque, to tell you that the angular acceleration is actually proportional to the angular displacement. And we can do this using the small angle oscillation, the small angle approximation, where the sine theta terms just approximately theta. And this way we can describe any physical pendulum as a simple harmonic oscillator as long as we know how far the center of mass is from its pivot point as well as its moment of inertia. And then knowing that it's a simple harmonic oscillator, you can derive a formula for its angular position as it oscillates from its max angular displacement and back. And in this case, the term for angular frequency is now dependent on the distance to the pivot point, the gravitational constant, and also the moment of inertia. And obviously, if you can find the angular frequency, then the definition of period and regular frequency follow as usual. There's a particular example of a pendulum, which is the torsional pendulum. So imagine you have like a thick foam disc. Maybe you've seen those like in swimming pools, they have those foam frisbees, and you suspend the middle of it by a wire and hang it from the ceiling. If you twist the disc, it's gonna unwind and twist all the way back. And ideally, it'll just keep twisting and untwisting and twisting itself cyclically. If you look at it from a rotational kinematics perspective, when you twist it, you are causing the string attached to it to sort of act on it, creating a restoring torque. So this restoring torque acts opposite to the direction in which you twisted it. If you twist the disk counterclockwise and you let it go, the disk's gonna untwist itself. It's gonna spin back clockwise, and that's the result of the restoring torque. This restoring torque is actually proportional to the angular displacement. So the more you twist the disk, the stronger the torque is, which leads to a stronger angular acceleration. So this is in fact undergoing simple harmonic motion. And this is true no matter how far you twist it from its equilibrium position. Obviously, if you twist it too much, you'll probably break the string, but still, you don't need to do a small angle approximation here. It works for all angles. So this is not, particularly the most crucial topic for the chapter, but it's an interesting case nonetheless. And you can then describe the angular position, velocity, and acceleration using the formula we've seen before. And now the angular frequency depends on not the Spring's constant, but a torsional pendulum constant, kappa, which again is a function of the material of the string. So the next topic is damped oscillations. And in the real world, there's no ideal harmonic motion. We've seen that these simple harmonic motion oscillators will oscillate forever, conserving mechanical energy. But as we know, in the real world, all objects experience drag and friction. As such, they lose energy. So whenever an oscillating system is losing energy, we say that their motion is damped. There's many forces that can act on moving objects and essentially take away their energy. For the purposes of this chapter, we're only going to be discussing damping forces that are proportional to the speed of the moving object. And the strength of these forces is determined by a coefficient called the damping coefficient. So you can have your restoring force present, and then there's also this damping force also acting on your oscillating object, which, if it's not too strong, you can actually still describe the oscillations using the formula shown at the bottom here. Now, if you look at the formula closely, the way that the angular frequency is defined for that damped oscillator, where there's a restoring force and a damping force acting on it, so this could be an oscillator like a piston submerged in a very viscous liquid, or a block spring system, exposed to really strong gusts of wind, then the angular frequency term actually is a bit more complicated than before. There's a term here, omega naught, which is the natural frequency, which is what you'd have as your normal frequency if it wasn't for the fact that the system's damped. And the next term here is essentially a term that accounts for the fact that there's damping occurring, so it kind of takes a bite out of your total frequency. So you'll note then that the formula for the position, right, as we've seen in the last slide, the formula for position has this exponential decay term, and essentially as time progresses, this term here gets bigger and bigger, and you still have your oscillating term, the cosine function. So what'll happen over time is you'll have your oscillations, but due to the presence of the damping force, the amplitude decreases over time because the system's losing energy to drag or to friction or to other damping forces. Now, we can use that description, that formula, if the system is underdamped, which is to say that the natural frequency of the system is much greater than the damping coefficient. So when that happens, like we saw, you still have oscillations. It's just that you lose energy over time, so your amplitude decreases, getting smaller and smaller. Then there's a critically damp situation where the coefficient of damping divided by 2 times the mass exactly matches the natural frequency of the system. And in this case, the oscillator won't actually oscillate. So as you can see in the red curve, this is a critically damped system where it'll simply coast off towards its equilibrium position, but it won't pass equilibrium. Now, the situation where the coefficient is bigger than that, the system's now overdamped. And again, the system will not oscillate in this case. It will even more slowly coast off to its equilibrium position. So the stronger the damping coefficient, the more damped it is, the longer it'll take to coast off to equilibrium, and it will not oscillate if it's critically damped or more. So the formula that we saw with the exponential decay term, that doesn't work anymore if it's critically overdamped. So what can we do then if, our spring block system will eventually come to a stop due to this damping forces? Well, we can obviously, add a piston to it to drive the oscillations to help it to fight off all the energy that we lose. So when we are applying a force to help the motion of an oscillator, whether it's a spring block system or a pendulum or a kid on a swing, we're creating what's called a forced oscillator. So the idea, right, if you think about when you're pushing someone in a swing, you're pushing them forwards the moment they're closest to you. And that way you're giving them a really big swing, a really big push at the best moment. If you give them a push when they're like swinging farther away from you, that won't help as much as giving them the push as you normally do when the swing comes back towards you and you push it and you push the swing then. So there's a timing, right? It's a particular moment in the period of the swing where applying a push helps it keep going. So let's consider that. Let's consider an oscillating system where it's damped. It's losing mechanical energy. There's throwing force. It's trying to make it oscillate, but it's losing to friction or to drag. So now we're gonna add one more force acting on the system, an external force, and it's gonna be periodic. So this force will vary with time. So that's why it's a function of time. There's a coefficient for the maximum force that can be applied, and then a sine term to account for the fact that its value increases and decreases over time. So this is kind of like the idea we talked about where you're applying the force to a kid on a swing. Well, you're not always pushing them, you're always pushing them at certain times. In this case, you're like always pushing them, just more or less over time. So in this system then, there's three forces present, right? There's the applied force here, or the external force. Now there's the damping force, sometimes called the retarding force, Fr, or just R. And then there's the restoring force, which is responsible for oscillations. So right, in the case of like the kid on the swing, this girl, like the swing's going, swing is essentially a pendulum, right? So you can think then there's a you can imagine then there's like a restoring force one way and a damping force the other way. So the push that you give the kid is there to kind of offset the damping force, right? Which is due to the heat loss from the swing and friction with air. So if we look at the formula now, we can still solve it and find a formula to describe the displacement of a forced oscillator with all these three forces present. And the formula actually kind of looks really similar to the one for a simple harmonic oscillator. Just note that the term here, omega, is actually the angular frequency of the applied force. And the amplitude is a bit more complicated, but it is constant. So once you have a forced oscillator moving, it'll eventually reach what's called a steady state, where it'll swing with a constant amplitude. But this amplitude is in fact a function of the amplitude of the frequency of the applied force, the natural frequency of the oscillator, and also a term to account for the damping. So the way that just remember this again, the formula is a mouthful, but essentially, if you look at the amplitude for a forced oscillator, you have at the top, you have this term here that this F naught is the maximum applied force. Then at the bottom, you have this term here, this omega squared accounts for the applied force. Then you have the natural frequency of the oscillator. So this accounts for the frequency that you'd have if it was just a simple harmonic oscillator. So that's the applied force. And then the third term here at the bottom accounts for the presence of the damping force that's kind of there to ruin your day, that as the damping force gets bigger, the coefficient gets bigger and the amplitude becomes smaller. Now, you'll note though that you have a term in the denominator that's omega squared minus omega naught squared. So it's a frequency of the applied force minus the frequency, the natural frequency from the restoring force. As the restoring force, as the applied force, as its frequency comes close to the natural frequency, that will give you a bigger amplitude. So we show that here. Pardon the noise. When the damping terms is small, the more damping it is, the more overall the amplitude decreases of oscillations. So it can also happen that as the damping gets smaller and the frequency of the applied force gets close to the natural frequency of oscillation, that will increase the amplitude. So you see here on the graph on the right that as the amplitude coefficient gets bigger from red to green, the amplitude overall decreases for any value of the frequency omega. However, when the applied frequency gets close to the natural frequency, the amplitude gets a lot bigger. So for an undamped system, the moment that the driving mechanism that creates applied force, if it has a frequency that's just about the same as a natural frequency of the oscillator, then the amplitude will be huge and we'll have something that's called resonance. So that's, again, resonance is when the amplitude of the applied force onto the oscillator matches its natural frequency. And this will create a really, really big waves, really big oscillations, which can be potentially dangerous, as it happened in 1940 when the Tacoma Narrows Bridge collapsed. So bridges, made of different plates linked together, essentially act as one big, imagine like a really big, thick string. So the bridge itself has its own sort of natural frequency to it. Its materials altogether act as an oscillator, even though it might not be noticed to the eye that it's vibrating. It still is vibrating with its own natural frequency. And on a really windy day, the winds themselves were sort of turning the bridge into a force oscillator. The winds the way they were flapping about, they were creating a driving force into the bridge, and their frequency actually matched the natural frequency of the bridge. So that created resonance, and the bridge started to oscillate. It started to move very wildly. And normally, engineers install what's called dampers in the bridge to reduce, the amplitudes of oscillations in windy days. But this particular bridge wasn't constructed properly, so without anything to dampen the oscillations, the amplitude got bigger and bigger. Now you can imagine that these are big metal pieces swinging pretty wildly. They're not meant for that, so eventually the bridge fell apart. Now, from what I understand, there were no casualties. I think one or two cars got lost in the water, but people were okay. And that takes us to the end of chapter 15. Hope you join me again next time, where we'll be tackling chapter 16. That's all for today.